Thank you for joining us. My name is David Martin, and I'm the Chief Client Officer at In Control Solutions. Thank you for joining us today. We've got what I hope to be an interesting show for you. Couple things. This is number 3 in the series on biogas plants and multiple feedstocks. If you want to see the previous webinars, you're welcome to check out our YouTube channel. You can find it by searching In Control YouTube, or you can find it from our website. Other things on the website of interest, we do have a info at In Control if you want to communicate with us. And the last webinar, we introduced what we call 1-hour expert advice. So for a reasonable price, we're offering anything you want to ask us about sensors, about anaerobic digesters, aeration modeling, please ask us, and we're happy to help you. Housekeeping things, if everybody would be kind enough to turn off your video and mute yourself. We can mute you, but we can't turn off your video so that we can concentrate on Alex's presentation. This event is being recorded, so if you don't like that, I'm afraid you'll have to leave yourself. It will be made available in the future on the YouTube channel. Those are the brief introductions. I would like to say that we're pleased to venture a little off our normal path, but for the last couple of years, we've been working hard in anaerobic digestion and biogas work, including a lot of temperature phase anaerobic digestion, looking at industrial biogas plants, how they operate, and one of the main subjects today is co-digestion processes. And that has been the major focus, analyzing and understanding what it means to put all kinds of different things into an anaerobic digester. So I would like to introduce Alex Rosenthal. He's an environmental engineer with us at In Control Solutions, and he is also the general manager of our newly incorporated U.S. office over in New Haven, Connecticut. Alex has worked in several areas of water resource recovery, including biological nutrient removal, fundamental biofilm research, and anaerobic digestion. And with that, I'll turn it over to you, Alex.
Great. Hey, thank you very much for the introduction, David. And welcome, everyone, to the What Did I Just Feed My Digester webinar. Really appreciate you spending part of your day with us. It's just going to take me a second to share my screen. Give me one moment. Okay, just a very, very brief personal background. The first thing I ever did as an environmental engineering student was grind food waste in the cellar of the engineering school at City College of New York. Everything from salmon carcasses to grocery waste to everything else. I was relieved that after 2 months of that, I was able to move downstream and work on biological side stream treatment, dealing with reject water. But 3 years ago, when I joined In Control, the CEO of our company, Live, and the CTO of our company, Oliver, said, guess what you're going to work on? Industrial biogas. And it has been a very interesting learning experience, and we've done some valuable work, and we're very excited about how it progresses in the future. So what we're going to focus on today is co-digestion. I'm sure that many of you are already familiar with what this is, but a brief definition. What we're looking at graphically is the multi-feed anaerobic digestion at a water resource recovery facility. So you've got your primary sludge and your waste-activated sludge from your treatment plant that's going into your digesters. But for various reasons, you may have spare capacity, in which case you go out and you try to source additional feedstocks to increase the rate of biogas production in your plant. And you're also coming up with a more sustainable strategy for dealing with solid waste that may otherwise go into a landfill. For those of you who are working with standalone industrial biogas systems, nearly everything that will be presented here is directly applicable to your industry. And I do think it's crucially important that we spend some time looking at the consequences of anaerobic digestion outside of its system boundaries, which is going to often, if not always, be a municipal or industrial wastewater treatment plant. Extending on this concept, it's not just co-digestion, but we're looking at anaerobic digestion modeling, and specifically anaerobic digestion modeling in a dynamic simulation platform called SIMBA Sharp. This is the software. We are the global resellers for this, and then we do quite a bit of model customization and expert consulting using SIMBA Sharp as a tool. And what we have are two distinct approaches for modeling anaerobic digestion. One would be in our SIMBA water library, and you can see a graphical representation of that above, where you have your mainstream of your water resource recovery facility, your clarifiers, your activated sludge tanks, and then you're generating residual sludges. And so then we would model the digestion of those municipal sludges and then look at those interactions of anaerobic digestion with the rest of the plant. But what was also developed several years ago, and it occurs on the same software interface, can be used in tandem with SIMBA Water, with a certain amount of customization, can even be connected to SIMBA Water models, is a library called SIMBA Sharp Biogas. And some of the key features of that is that what it allows is more analysis of the complexities of multi-feed anaerobic digestion. So if you were to have a facility that took in 4 or 10 or 30 or 100 different feedstocks, we would need to go through the effort of characterizing what the chemical composition of those feedstocks are and the digestion kinetics of those feedstocks. In addition to the feedstock side, which is a big focus of today's talk, additional features of SIMBA Biogas is at the downstream end with the biogas handling. So we have a system of piping network, valve blocks, compressor blocks, and gas storage blocks, which can be really useful for the dynamic modeling of how you actually handle and get sort of the most profitable recovery of that biogas for your purposes. And then the last thing that I want to go into before getting into the technical content of this presentation is we strive to make these webinars as interactive as possible. We want your feedback, input, participation, etc. And so with that in mind, I would ask, do you have a cell phone, or alternatively, do you have a second monitor? Because what we're going to do at different parts of this presentation is actually switch over to an online utility that we've been using quite a bit called Mentimeter. And let me just get back to the first slide so that there's no spoilers. And what you can do, if you look at the top, you could just open up a web browser and you could go to www.menti.com. And all you do is you just punch in that 6-digit code. It's anonymous. It's not tracking you. It's not collecting a whole bunch of personal data. And then you can participate in some of these interactive online polls. And so for right now, just want to ask a very simple question just so we can get a sense of how much participation we're going to get into this. How many of you want to participate in the interactive sections? You can answer yes, or you can answer leave me alone. I just want to chill out. I don't want to have to do this stuff. Okay, this is looking pretty good so far. I'm just going to open up the voting for just another minute or two, just so we have a sense of what quantity of responses we should be looking for as we proceed through the rest of the webinar today. All right, well, if no one else is going to vote no, I am. All right. Okay, so right now we'll just consider 20 votes to be the threshold for a completed question. So I'm going to jump out of this for the next few minutes, and we'll get back into the PowerPoint portion of the slide.
Alex, there's 36 people, so that's 2/3. That's pretty good.
Yeah, that's better voter turnout than I'm accustomed to in other settings. Okay, not bad. All right, so we'll start a bit with some fundamental stuff on anaerobic digestion modeling as well as feedstock modeling. So sure, many of you are familiar with this diagram, have seen it on conferences. What this is sort of the conceptual schematic of the anaerobic digestion model number 1, published in 2002 by Batstone and several other researchers. And so just to sort of take you through what this is representing is that your feedstock is often, though not always, physical aggregates of complex organic matter. And that could be a flock of bacteria coming from your clarifiers. It could be a rotten piece of meat. It could be some moldy bread. It could be a candy bar. Okay, and so the first step in the degradation of that material is actually disintegration, where this complex piece of organic matter is being broken down physically into smaller and smaller bits that then could undergo chemical or biochemical extracellular hydrolysis. Okay, so disintegration can be painfully slow. That's how it's modeled in ADM1, and you'll see that that's how we actually model it in our in-house digestion model. But what often happens when you hear people talk about digestion is that they're conceptually lumping hydrolysis with disintegration. So for instance, something called thermal hydrolysis process is in reality actually a thermal disintegration and hydrolysis process. And when folks say that hydrolysis is often, if not always, the limiting step in anaerobic digestion, in our expert opinion, what we think they're saying is that disintegration and hydrolysis together ends up being the limited steps, the rate limiting steps in anaerobic digestion. Once you've hydrolyzed your polymers, your carbohydrates, lipids, and proteins into their monomers, what you're generating are sugars, long chain fatty acids, and amino acids in this model. And then you start going through acetogenesis, where you're breaking down those monomers into short chain volatile fatty acids. And then you're also getting the release of ammonia from those amino acids. Next, you have the process of acetogenesis, which is the generation of acetic acid and hydrogen gas and some carbon dioxide. And then the anaerobic digestion model is simulating two different microbiological groups of methanogens. One is a group called hydrogenotrophic methanogens. These eat hydrogen gas and respire CO2. And then you have the acetoclastic methanogens that break down acetic acid, both of them generating the methane that we could then recover either for purification into biomethane or the generation of electricity, or in a worst case scenario, you just flare it. Okay, I would just want to say with the caveat, is the anaerobic digester model one the whole truth? No, absolutely not. Anyone who's on this call who has worked with digesters or who has studied microbiology knows that the microbiology, the consortia, and the types of metabolic functions in these digesters is really complex. You have other elements that are being transformed apart from just the carbon and the nitrogen. You have sulfur and phosphorus and so forth. But the second point is that even with those simplifications, is anaerobic digester modeling illuminating and useful? Yes, absolutely. It's a powerful stoichiometric and biokinetic model to predict the dynamics and to perform dynamic mass balancing in anaerobic digesters. Okay, what we have done is we've made an adaptation of the anaerobic digester one. The main difference is that we allow a more detailed fractionation of that complex organic matter into slow and fast disintegratable carbohydrates, fats, and proteins. And what this allows us is distinct characterization of each feedstock that you're modeling. State variable concentrations affect the process kinetics. So you can see the 42 state variables and then the 30 dynamic processes. And then your processes are going to affect your state variable concentration. So a bit academic, but if you were to use SIMBA Sharp, this is the model that would be underneath in SIMBA Biogas. You can open this file, you can edit it, you could add new processes, new state variables, change parameters. We often don't recommend changing those parameters, but it is an open software, you could do that. And what a dynamic simulation platform does, like SIMBA Biogas, is that we're doing a numerical integration of this entire process matrix to predict the dynamic behavior of an anaerobic digester. So then the question remains, okay, I've got this digester and I'm throwing all this organic stuff into it. How do I turn these glass jars of sludge into variables that are compatible with this anaerobic digester? Essentially, how do I map things that I might measure in a laboratory to this row of 42 state variables? And so what we have is an approach to model feedstocks in SIMBA Biogas where we answer three principal questions. What is this feedstock made of? So what is its organic composition? The second that we won't go into in too much detail on this call, but we can talk about offline if anyone's interested, is what is the buffer chemistry of the feedstock? So ammonium and bicarbonate, et cetera. And then the last is we know what's in the feedstock, but we need to know what is the degradability of the feedstock. So three main things. So to answer that first question, we actually go way back. We go to the old school and we use the proximate system of analysis of feedstocks that was first developed in 1860. Now, this has been debated extensively over the last 160 years, but it holds up really well, and it's a very common system of analysis for animal feedstocks in the nutritional sciences field, and then now for anaerobic digestion modeling. And essentially, you're breaking down your feedstock into 6 main components. You have the moisture content, or the water. You have the inert component, the ash, so what's left over after you put it in a furnace. You have a simplified analysis of total protein, where you're actually measuring the total Kjeldahl nitrogen and then multiplying that by a factor. You have an estimation of the lipid content or the fat content of your feedstock, which you can measure by different organic solvent extractions. And then you have 2 fractions of carbohydrates. You have your fiber, and then you have your non-fibrous carbohydrates, which is called nitrogen-free extract, which is essentially whatever organic material is left after you've measured everything else. Okay, so we'll move on from what's in the feedstock. So let's say you've got an estimation of how much protein, fat, carbohydrate, ash, and water you have in your feedstock. What you wouldn't know yet is whether you can throw that substance into an anaerobic digester and actually generate methane. And so what we rely heavily on when we're modeling feedstocks is on the batch kinetic assay that's very common. It's called the biomethane potential test. The way it works, for those of you who aren't familiar, is you take a whole bunch of sludge from your anaerobic digester, you add a little bit of your feedstock, you put a cap on it, you keep it at the same temperature as your digester, or maybe at a standard temperature, 35 degrees Celsius, and then you see how much methane is evolved from that bottle over time. Okay, on the left, you see a very simple apparatus for the measure of it. You can procure much more advanced systems that are integrated with computer systems and bubble counters and so forth. But this captures the essence of how a BMP test works. And if you look over at the right, what you're seeing now, there's a lot of other caveats to how a feedstock might perform in a BMP test, but what we just want to take a look at is a 2x2 matrix of, one, what is the extent of degradability, how much of it can digest into methane, and then how fast is that digestion of the feedstock to methane. So in the upper left-hand corner, you see something with low and slow degradability. So up top, we're looking at that black dashed line, and we're saying, okay, if my COD in my feedstock was 100% biodegradable, that's how much methane I would expect to get this. And you see in the low and slow degradability, you're really not even asymptoting out in terms of the methane you produce until day 50 or even later. And that's going to be higher than the typical SRT of an anaerobic digester. So one, this feedstock is not going to give you all that much methane. It looks like only about 200 liters of methane per kilogram of volatile solids that you add. And you're not going to actually generate that methane during its transit through an anaerobic digester. Okay. If you were to compare that with something that was low and fast, still, you're only going to peak out at about 200 liters of methane per kilogram VS, but you're asymptoting out before 20 days. So this is something that's going to degrade relatively quickly and is going to reach near complete degradation at typical SRTs in your digester. And then just to wrap things up, you can take a look at, say, something that has a very a high extent of biodegradation, where you may be able to get upwards of 80, possibly even 85% conversion of the COD in your feedstock to methane. And it's just a question as to whether that's something that disintegrates and hydrolyzes very slowly, as in the case of the upper right-hand corner, or whether it's something where you could actually expect to yield nearly all of the available methane from that feedstock in the time that it spends in the digester. Our approach when we're setting up these feedstocks is actually to, let's say in this instance, we grabbed a paper from Kabouris in 2009 where he looked at primary sludge, waste activated sludge, and fats, oils, and grease. We actually digitized their batch kinetic data from their BMP test. And then we have a simulation in SIMBA Sharp where we faithfully replicate the VDI recommended protocol for the biomethane potential tests. And then the parameters in our feedstock model for how much of this is fast disintegratable, how much of it is slow disintegratable versus how much is already disintegrated and will go through hydrolysis, those parameters can be tuned to optimize the batch kinetic curve fit that you see in red relative to the blue. And so in this way, we take those state variables that give us protein, fat, carbohydrate content, total solids content, ash content, et cetera, and that tells us what's in the feedstock. And now we can have a very well calibrated sense of how fast is this feedstock going to degrade and what's its extent of degradation going to be in our model. The other images just give you a sense of I guess some of the complexity of what this model would look like in our simulation drawing board. A lot of lines, looks like spaghetti, but with a little bit of time, you can sort of understand how it works in practice. Okay, so I know that if someone was showing this to me, they'd say, that's great, but generating that data for a bunch of feedstock sounds like a lot of work. And I agree with you. And in some of our initial projects, it was an immense amount of work. In fact, even in municipal wastewater modeling, it's an immense amount of work just to get proper characterization and calibration of your influence. So imagine doing that not for one influent wastewater stream, but for 50 or 60 feedstocks that are coming into a facility on a regular basis. What we discovered, and I think this is something that a lot of you probably know, is that if something rots on the ground, someone has probably tried putting it in an anaerobic digester and written about it and published it. And so, you know, if you don't believe me, this is just one paper from 2011. It's from Labatut, researcher, I think, in New York State. And this is just one paper, and they've got 30 mono and co-digested feedstocks. And some of the examples to highlight is, imagine a mixture for whatever reason of 75% manure and 25% mouthwash. They've measured the biomethane potential on that. They went to Oneida Lake, which is one of the finger lakes in upstate New York, and they grabbed some lily pads, which happen to be frog bit, and they digested that to see what the biomethane potential is. And they did a whole bunch of other laboratory analyses. And so the amount of published feedstock data over the last several decades is massive. And so what we've done as an internal development effort is we are continuously updating a database of anaerobic digester feedstocks. And more importantly, we're going through the effort of data sanity checks, identifying discrepant data, and standardizing that data in terms of units and making sure that we have the variables that we need so that then we can run it through the very standardized, very routine calculations that we would use on those laboratory data to generate the state variables we need to characterize that feedstock in a SIMBA biogas model. And so there are a lot of other use cases for a software like this. But in terms of how it relates to what we're talking about today, which is the predictive modeling of biogas plants in SIMBA Sharp, the most important use case in my mind is to be able to have lab data at your fingertips and not have to take out a notebook or a calculator and calculate all those parameters every single time you want to set up a SIMBA model. And so that's what this software is doing for us, is it just automates that process, makes it a lot more efficient. Okay, so before going on to the case study, actually want to do something a little different. We're just going to have to see whether this actually works, because have not done it with this big of a group. This is actually a game. So we're going to compete in a quiz. The questions are not too crazy. You can pick any name you want. You can use the default name, or you could punch in Dr. Fauci, you could punch in Beyonce, anything you like. I'm going to use the default name Joanna, and I'm a koala bear. I won't answer. I don't want to cheat because I wrote the questions. Okay, so we got 26 participants. I think we're ready to start this quiz, okay, based off of what we've been going through. Okay, answer fast to get more points. Which will digest faster? A piece of raw meat or sugar water? Okay, I was trying to be generous. We could take our time, but it looks like the text in the question was slow. There were only 2 answers, so it looks as if we've got a complete set of answers. And let's see. Okay, 20 out of 24 got it right. Yes, sugar water. The reason being is that a piece of raw meat is, again, a complex piece of organic matter. It's going to have to undergo disintegration and hydrolysis before it will go through any of those other subsequent steps of anaerobic digestion. Whereas sugar water, this is already sugar. It's an organic monomer, so it's a carbohydrate that's already undergone hydrolysis. Okay, so let's see who is in the lead. It looks like Heartstorm beat out the boss by probably about a millisecond. Okay, let's move on to question number 2. Which feedstock would release more ammonia into the digester during anaerobic digestion? Again, raw meat or sugar water? Okay, looks like we've got a complete set of answers. Just need a few more seconds before the question time's out. And perfect score, 27 out of 27, yes. For those of you who eat meat, I do, contains a lot of protein. Sugar water, to my knowledge, contains no protein. And it's the degradation of proteins in a digester. Proteins contain the nitrogen. That's what's going to release ammonia into the digester. This can have an impact on feedstock selection, particularly if you're concerned with the recycle ammonia loads back to your water resource recovery facility. Let's see, do we have a new leader? The boss has tied Heartstorm. Okay, well, at least on question 2, Heartstorm still has 2 points. Lead. Okay, question 3. There's a total of 5 questions. Believe me, I'd be perfectly happy to do this for the rest of the webinar, but we do have a bit more technical content. Which has a higher biomethane potential? Hope most, if not all of you, know what these foods are. You've got New England clam chowder, a very hearty soup with potatoes, ham, clams, cream, and you've got low-fat vegetable soup, water, vegetables, maybe salt. Okay, yes. Okay, maybe a little bit culturally biased. I do live in Connecticut, New England, but yes. If you want to know which one is going to release more methane during digestion, a helpful thing to do is just take a look at the nutrition label, look at the calories, look at the fat, the protein, the carbohydrate content. That's going to be much higher in something like New England clam chowder. Okay, question 4. Well, let's take a look at first at who's in the lead. Uh-oh, Boss has claimed first place. Heartstorm has slipped to 3rd. SA is up to 2nd. Okay, question 4. Which has a higher chemical oxygen demand? 1 kilogram of plastic bottles or 1 kilogram of the Coca-Cola that was poured from those plastic bottles? Okay, we've got our first tough one. This is chemical oxygen demand rather than biological oxygen demand or biomethane potential. Plastic is essentially 100% organic matter. So it is going to have a very high chemical oxygen demand. If you were to incinerate it, I don't recommend that you do, you would release flames and a lot of heat. Whereas with Coca-Cola, even though it does have a high sugar content, it still is mostly water. So the actual organic content of Coca-Cola is relatively low compared to plastic. So let's see, I got a feeling that whoever answered that first is probably going to hit first place. Okay, SA is pulled into the lead. Okay, all right, last question, and it's related to the previous one. Which has a higher biomethane potential? Again, 1 kilogram of plastic bottles or 1 kilogram of Coca-Cola? Yes, Coca-Cola. Coca-Cola is biodegradable. Generally speaking, plastic is not. There may be some newly developed plastics that are biodegradable. If that's what you were thinking when you answered it, I apologize. But in general, I would not recommend putting plastic bottles into your anaerobic digesters. There are companies, especially equipment manufacturers, who sell a lot of pieces of machinery just getting all that plastic crap out of your feedstock so you can put them into your digesters without problems. Okay, so who is the champion of our anaerobic digestion quiz? It is Mr. Anderson. Okay, Mr. Anderson, if you want to reveal yourself, your identity at some point during this webinar or after, please do so. But congratulations and excellent job on our co-digestion feedstock quiz. Okay, back to more serious matters. Right now, what I want to do is go through actually a hypothetical case study of co-digestion at a municipal water resource recovery facility. Okay, so we'll lay out some of the facts, the base case about this facility. What we have is a flow rate of 20,000 cubic meters per day, is a rough estimate. That's about 50,000 people, or a town of 50,000 people in the United States. A COD load of 12,000 kilograms per day, and a total Kaldol nitrogen load of 1,000 kilograms per day. We've got our activated sludge process, and if you have tuned in for webinar 1, which was Oliver talking about aeration system modeling, and you run this facility, you've already optimized your aeration system, you've got really good diffuser distribution in your 2 aerobic tanks. You've applied most open valve control so that you can supply air at the lowest possible energy. Then you followed up by watching Live's webinar, which was a few weeks ago. You've got your online sensors deployed, your dissolved oxygen sensors and your ammonia sensors. They're commissioned, they're well maintained, they're measuring accurately, and you're confident enough in them that you wired them up into an ammonia-based aeration control system. And so you've got a really nicely operating plant for total nitrogen removal. Okay, and now in your path towards optimization, you're looking at your solids handling. And what you've got right now is sludges from your waste activated sludge line and your primary sludge line of 700 cubic meters per day, COD of 7,000 kilograms per day, and a total Kaldol nitrogen load of 350 kilograms per day. We zoom out a little bit to take a look at the solids handling line. We've got a thickener. Downstream of that, an anaerobic digester. Then you've got dewatering of your digested sludge, and then you're recycling your centrate and your thickener recycle back to your activated sludge plant, and you've got to dispose of your biosolids. Okay, you take a look at just some of the basic operating conditions of your digester. Your solids retention time is 27 days. Your organic loading rate is 1.6 kilograms of volatile solids per day per meter cubed. And if you take a look at your biogas expressed as COD, because methane has COD, you can combust it and see how much oxygen it has. If you don't believe me, you're recovering about 25% of that relative to the influent COD load. Okay, and then a couple of things to look at in terms of anaerobic digestion and some of the recycle loads. Relatively small flow rate. It's kind of big here because you're also looking at the thickener recycle. Your COD load is relatively modest. What you've got to be careful about is you're going to be recycling quite a bit of nitrogen back into your mainstream plant. And so in this particular case, it can increase the load back into your activated sludge process by about 18%. Okay, and then you've got to dispose of 14 cubic meters of biosolids each day. So maybe about 15 or 16 short tons. Okay, so we take a look a little bit closer at the solids handling line, and these are all simulations in SIMBA water. We do a little bit of calculations with some standard assumptions and constants available in the literature. Assume 35% of that methane is going to be recovered as electricity in your combined heat and power unit. And so this facility that treats wastewater for 50,000 people is we're predicting that it's going to generate 3,700 kilowatt hours per day of electricity. And that's, in the United States, that's about enough for 125 households in the United States. So last session on the Mentimeter interactive software, most important question of the day. Give me just 1 second. Do you want to make more biogas at this facility? Okay, I thought so. Okay, but let's see, we're at 1:36, so we've got a little bit of time. So let's answer an open-ended question. This one isn't multiple choice. I'm gonna jot down a couple of answers. Maybe some of my colleagues at In Control will answer. If you guys have any thoughts, if you're experienced with this, or if you've been studying it and you have some thoughts, and you feel comfortable, why don't you just type in some short answers? So to basically, what do you need to consider before pursuing co-digestion at this water resource recovery facility? Okay, so we've got the value of the byproducts. So I'm assuming by byproducts, you're talking about the biogas, potentially talking about maybe potential value of the biosolids, or maybe the cost for disposal of those biosolids. I'm just going to jot down, let's see, return nitrogen loads, stable feedstocks, COD to N ratio, logistics and CapEx, effect on side stream to liquid side. Yeah, that's a good point. The BMP of the co-substrate, the organic loading rate of your facility. Yeah, feedstock treatment. Are you going to need pre-treatment, or is it going to come to you ready to load? CHP and purification capacity. Yeah, that's a good one, because how much capital investment you need to make to be able to deal with higher gas concentration. Okay, let's see. Proper and safe receiving station. Yeah, that's a good point. Is your facility, are you set up so that you could take 10, 20, 30, 40 trucks coming in and out of there every day? Okay. Let's see, are there any other uptime of digester and whether co-digestion can affect the biology and increase downtime? Okay, so the idea that maybe you won't be able to operate stably anymore if you start loading it more aggressively with co-digestion feedstocks. Okay, no, this is really good, and I appreciate everyone who was able to provide input. In the interest of time, I'm gonna jump back to the presentation and wrap things up, and then maybe we'll come back to this during the Q&A session if any folks want to do some more detailed follow-up on some of these comments. Okay, so we've identified that at least on an organic loading rate and solids retention time basis, it looks as if this digestion system has spare capacity to take in co-digestion feedstocks. And so let's say that you've also satisfied many of the other criteria that we collected on that interactive slide just a couple minutes ago. One of the next things that you're going to need to is figure out, well, what's available to me to load into this digester. So for starters, let's just take a look at what our baseline is. We've got combined thickened water resource recovery facility sludge coming in at 43,000 cubic meters per year at a volatile solids content of 4% by weight, a moderate to low BMP at 295 normal meters cubed of methane per ton of VS. You got a carbon to nitrogen ratio of 10 grams of carbon to nitrogen. And then we take a look and we see what's available in our immediate vicinity. What are people trying to get rid of where we might be able to help them out? Okay, so One, and I've seen this in a couple of case studies. For some reason, some people have access to poultry blood. I'm surprised because it kind of has value as a fertilizer, as blood meal. But I think sometimes maybe it's either off spec or people are producing more blood than the fertilizer industry can handle. So let's say you've got 2,900 metric tons per year of poultry blood available. The reason that I would consider this a very high value feedstock is that it's relatively uniform. You're not going to have much of a risk of a bunch of like forks or other stuff that you might see in consumer waste. A really high organic content. So on a wet weight basis, it's 20% organic solids. And from the literature, that's a pretty good biomethane potential of 500 normal meters cubed per ton of VS. The one thing to look out for is blood has a lot of protein in it. So a C to N ratio of 5 is really low. That means you've got a lot of nitrogen. Okay, the next one we'll evaluate is grocery waste, or this could be similar to say like a source separated organic, 3,700 metric tons per year. Still a relatively high volatile solids relative to our combined thickened sludge, a more moderate biomethane potential, and a more moderate carbon to nitrogen ratio. Another one that we see people load a lot into digesters are fats, oils, and grease. One of the things to pay special attention to on this feedstock is that volatile solids can be anything. We've seen fats, oils, and grease with organic contents as low as like 1% or less. And then sometimes you just have like used vegetable oil, which is 100% organic. There's very little water, none at all. Really high biomethane potential because it's fat, so just very high caloric content. Virtually no nitrogen. You may just have some impurities that contribute a bit to a small protein content, but really you're just looking at almost pure carbon in this facility. And then finally, something that you see a lot of in the food production business is dissolved air flotation sludges. Oftentimes, these have a relatively low volatile solids content. But in this particular example, if this is coming from, say, an animal processing facility or dairy processing facility, you may very well have a fair bit of fat in it as well as protein. So you're going to have a pretty high biomethane potential. And if you've got a lot of protein in it, again, similar to poultry blood, you could be looking at a high nitrogen content in a feedstock such as this. So the first thing that I would do with this information after receiving it is to run a steady state analysis and say, okay, if I just load this at an average constant rate, what am I going to expect to happen? Am I going to stay within target ranges for solids retention time and organic loading rate? And what would be an approximation of the biogas that I could produce? What we predict in SIMBA, based off of the data that was in the previous slide, is this would result in a decrease of solids retention time from 27 days down to about 20 days, and an increase in organic loading rate up to 2.4 kilograms volatile solids per day per meter cubed. And if you compare that to what's in a lot of Water Environment Federation literature, we're staying within our target range for mesophilic anaerobic digestion. Now, there are folks who go a lot more aggressive than this. But if you're a municipal facility, you may be well advised to try to stay within these target loading rates. And then we would predict a 70% increase in methane production rate relative to the municipal sludge digestion base case only. So you could walk away from this and say, great, let's do it. You may be getting some significant gate fees for taking in these wastes. And then you're getting a 70% increase in biogas production, and if it scales linearly, you're going to get a 70% increase in electricity generation. So fantastic. But the thing that we really need to be aware of, and it's something that we see in virtually every project that we work on, every anecdote that we hear, is that feedstock loading rates are rarely, if ever, constant. And it's due to two important facts. One is that people don't like to work on weekends. I know I don't, and most people don't. So what's often going to happen is your co-digestion feedstocks are going to come in on weekdays, often, not every day, but just a couple days per week. And then you're going to get this delivery gap on Saturday and Sunday. Okay, and then the other one that's more important, and much of it is encompassed in our modeling approach, but not all of it, is that people who generate waste are not in the waste generation business. They're beverage companies, or they're cafeterias, or they're other food production companies. the waste is just an unfortunate byproduct of their business. So it's not necessarily going to be uniform, and it's not necessarily going to be available on a regular basis. And so this poultry blood is a representative example of something that you only get sporadically. So you may go 30 or 40 days without getting any, and then all of a sudden they have a problem on their production line, and they've got to get rid of just like a ton of poultry blood for 10 days. And then they fix whatever is going on at their facility, and then you don't get it for a long time. So when we consider the actual irregular dynamics of loading of these digesters with co-digestion feedstocks, and then we factor that into our models, things can go just absolutely haywire at a co-digestion facility. And so you just wait for it. You can see the clock. We get to 10 days, and all of a sudden that poultry blood goes in, and we immediately violate our organic loading rate constraint during periods of this high poultry blood loading. And if you look at the literature, or you hear anecdotes from your colleagues, or maybe you have these anecdotes, it's clear that both overloading, and in particular rapid swings in organic loading rates and rapid swings in organic load composition, are the most common causes of digester upsets. Okay, so here, I mean, in this case, and this is not an unrealistic case, this happens. Somebody might actually triple their organic loading rate immediately, because they had an opportunity to get a strong feedstock, they took it, and they may not have sufficient storage capacity at the upstream end, so they just got to put it in their digester. So even if this didn't totally devastate your digester, let's say your digester for whatever reason can handle that swing in load, what you're still going to get is a rapid swing in biogas production. And that's really difficult to match with your downstream electricity generation equipment, or your biogas upgrading and purification equipment. And what this often, if not always, leads to is a lot of biogas flaring. So all of that increased revenue, or increased electricity, or increased sustainability that you expected to have at your plant basically just goes right into your flares, because your equipment was not designed to handle those swings, and your system or your operating strategy may not be ready to deal with that much volatility in loading rate. So that concludes that hypothetical case study. Just one last bit of technical content before wrapping up this presentation. We are doing this work. So what I'm showing you now is a case study that we're currently working on. This is a large North American co-digestion facility. They're doing dynamic loading of 17 unique co-digestion feedstocks, along with their primary sludge and thickened waste activated sludge. We're going to provide a lot more detail on what this work entailed and what the results of it are during WEFTEC. So we've got this abstract submitted and are working on the manuscript, so that will be available for you all very soon. But the key takeaway from this study is that when we do a rigorous job of looking at client feedstock data, and then comparing that to literature feedstock data, and then accurately simulating the delivery dynamics of those feedstocks to the plant, we can do an excellent job predicting the biogas production dynamics. So we're pretty spot on, and these are preliminary results. And so the question that remains, and it's an eternal question, is, okay, we can predict biogas production. What is the value of that? Well, the value goes back to the flaring that you see, is that plants, generally speaking, cannot handle this much volatility, this much up and down in their biogas production rates. Not the spikes during weekdays relative to weekends, and not also some of these higher resolution peaks that happen when you get some rapidly biodegradable feedstock. So the question is, and it's something that we plan on working on more, is what sort of design and operating strategies can we work on to try to turn that red and black jagged line into a flat line, so that people who are doing co-digestion can recover a higher percentage of their biogas for profitable, useful purposes. Okay, so to wrap up, three main takeaways. Co-digestion can obviously significantly increase biogas production at water resource recovery facilities, but it also introduces greater complexity and risk to facility design and operation. And one of the main reasons to that is that you're taking in a whole lot of different feedstocks, and that those are coming in discrete batches. And the people who are providing that waste for you are not necessarily in the waste generation business. So you get what you get when they've got it. Okay. Second is that there is a vast body of knowledge on predictive modeling of anaerobic digestion and the characterization of feedstocks. And so we can go back to laboratory protocols from the 1800s that have been changed only very little over the last 160 years for the characterization of feedstocks. We can apply that knowledge about feedstocks to input those state variables into dynamic models such as ADM1 or our in-house model, the ADM1DA. And so when we standardize that information and when we encapsulate it into a piece of software, we can start making very good dynamic predictions of how these complex large facilities function. And that's really the key purpose of what we're doing in SIMBA Biogas. And then the last takeaway, it's really more about us and what we do. In Control Solutions, our company, we've developed a lot of expertise in this area, as well as the water resource recovery area. We do quite a bit of consulting in this space. And then we also have software tools, and we customize software tools to support the deployment and optimization of anaerobic digestion processes. And so that can include software tools to organize and clean up and augment data for looking at co-digestion feedstocks. It could be organizing data and consolidating data that's generated at the plants themselves, operational data. Our main focus of this talk was looking at dynamic predictions of multi-feed biogas plants, so doing diagnostic and predictive analytics. And then what we see as sort of the culmination of all those efforts is that once you predict, you can control. And so a lot of what we do is we develop control systems, we use models to help develop those control systems, and then we encapsulate all of that software and expertise into a software platform, a monitoring control platform that we've recently rebranded as Ops Control. So if anyone is interested in these tools or interested in consulting services on co-digestion, I'd invite you to contact us directly. We'd love to talk with you about it. And I would just close by saying thank you all very much. I really appreciate the time you spend. I know that all of us are likely spending a lot of time on online calls. So it means a lot to us that you were able to spend an hour with us today. So thank you all very much.